Hi, for this lesson, I want to take you back in time to Tuesday, the 30th of January 1607, about 9 o'clock in the morning. Because that particular point in history perhaps gives us a potential warning for the future. Let me explain a little bit more. Because in this lesson, I want us to explore the idea of whether there was a tsunami in the Bristol Channel back in 1607. For this lesson, you're going to need your handout entitled The Bristol Channel Tsunami. And what we're going to do is we're going to review some of the geological evidence for this possible event and perhaps try and draw our own conclusions from it. Okay, then, let's go. Let's start by looking at the channel itself. This is a topographic and bathymetric map, so it's showing the height of the land and, crucially, the depth of the Bristol Channel. We know already that the Bristol Channel is a flooded river valley, formed largely when during the last glaciation, where sea levels would have been lower, and the early River Severn then was eroding this valley. And as sea levels rose, then the seas inundated the channel, flooding the lower parts of the valley right the way up towards Gloucester. How would you describe then the topography of the channel itself? What does this map and what does the contour map on your handout actually show us about this stretch of the sea? Annotate your map now with your observation. We can see from this map that if we look first of all at the shape of the coast here, you can see that the channel clearly narrows as we go towards the east. We can also see that the depth of the channel decreases as we go to the east. Now, if we combine those two factors, what we have is the Bristol Channel funneling the sea as it goes eastwards. Now, this has a modern day effect. We can see these huge tidal ranges in the Bristol Channel. It's the second highest tidal range in the world, second only to the Bay of Fundy in Canada. We also see spring high tides, so much water being pushed up this funnel-shaped channel that we end up with a tidal wave, the Severn Bore, heading up the River Severn. But that happens in a predictable way. We know when that's going to happen, and we know as well the extent of that tidal wave. The events in 1607 went beyond that. In particular, I want us to think about this place. This is Burnham-on-Sea on the Somerset coast. Beautiful little coastal town. But if we have a look at some of the effects there, that might perhaps help reveal what was going on. This is a tide time graph predicted for January 1607. If we think about this particular flood, it's occurred about 9 o'clock in the morning. Obviously, exact timing is difficult to determine, but from the historical records, it's about 9 o'clock in the morning. From the tide predictions, we can see that coincided with a high tide event. Not just any high tide either, this is a spring high tide. So about as high as the tide in the channel can get, 12 metres high. So any event occurring that coincides with high tide will obviously magnify the effect of that high tide. The channel is already full of sea. We find evidence of flooding around the coast of the channel, and we see evidence of this that suggests quite high waves affecting the low-lying areas of the Bristol Channel. So you can see coastal areas, for example, around Swansea and North Gower. Bigger effects then on the Gwent levels between Cardiff and Newport, and in particular in the Somerset levels, as you see going inland there from Burnham-in-Sea, and also up the Severn Valley. If we look at some of the geological evidence for this, though, in Dunraven Bay at Southern Down, if you look carefully at some of these blocks of rock that have fallen off the cliffs, you notice something relatively unusual about them. The geologist, you can see, is standing on top of loose blocks of rock. So what you're looking at here isn't dip, but you can see an alignment of those boulders. They're actually showing a sedimentary structure we call imbrication. Now, we need to think about what would imbricate boulders like this. What would have the energy to move these boulders and to tilt them, stack them up, if you like, in a way that presents the most hydrodynamic shape to whatever's moving. Now, this can really be one of two things. It could be a storm wave, needs to have a lot of energy to move these boulders, or potentially a tsunami wave. Let's look at some of the data from other places around the channel. Now, this graph that you have on your handout shows us the size of boulders in a way in terms of the size of the wave that would be needed to move boulders of the sizes found in these places. So, for example, on the coast by just south of Cardiff at Sully Island there, you can see that a wave 3.5 metres high would have been needed to move the imbricated boulders that are found in that location. Now, if we try and add something to this diagram that sort of summarises this, so we need to try and organise this data a little bit better. Let's draw some contours of wave height. So we can see that these boulders, to be imbricated, on a line from Ilfracombe in North Devon up to Gower, the waves there would have to be about 4 metres high. If we go further along the coast there to the area around, for example, Ogmore, we need about 5 metre waves. And then further up the channel there, as we're getting closer to Bristol, we'd need 6-metre waves. So how is the wave height changing, indicated by the imbricated boulders, as we go easterly along the channel? Clearly it's getting higher. If we plot this on a graph, we have the boulders plotted against wave heights. Now, I do apologise for this graph because, if you like, it's sort of the wrong way round. Okay, on the right-hand side there, we've got the outer Bristol Channel, so that's further out to sea. On the left-hand side there, we've got the eastern part of the channel as we head up into the Severn Estuary. But if we have a look at some of the data here, let's start with this. These are the storm waves. So this is the maximum storm waves that have been measured in these different parts of the channel. So in the outer Bristol Channel, we've had 10-metre high storm waves. Yeah, pretty big, pretty scary. Okay. As we come to the inner part of the Bristol Channel, in the area, for example, around the Vale of Glamorgan, we have a maximum wave height of 4.7 metres. By the time we get to the Severn Estuary, it's a 3.5 metre storm height. So we can see that the wave heights of the of storm waves decrease as we go further east, as we get further, if you like, inland, which makes sense because those as we go further east, the channel is becoming more sheltered, less exposed to Atlantic storms. But that's not necessarily the pattern that we see with the boulders. Let's come back to that in a moment. Also looking at this graph, if we look at the wave heights, on the left we have the equivalent of tsunami wave heights. On the right, we can see the equivalent of storm wave heights. To make sense of this, let's pick one of these data points. Let's pick the boulders, for example, we find at Sully Island. Now, the boulders at Sully Island, to move them, we'd need a tsunami wave of about 3.5 metres, maybe just a bit more than 3.5 metres. For a storm wave to move the same size boulder, we need a wave that's maybe 14 metres high. What's the relationship between these? What does it tell us about these two different types of wave? Clearly, the tsunami wave is more powerful, has more energy to move rocks around than storm waves. And we can even establish a mathematical relationship between them. You know, the tsunami wave is going to be about a quarter the height of the equivalent storm wave. So if we look at this data and we look at the Sully Island boulder there, which is a little bit of an anomaly, as is the boulder that was discovered at boulders measured at Scare Point. But if you look at the Sully Island boulder, the maximum wave height measured around Sully Island is 4.7 metres. If that boulder's been moved by a storm wave, it needs to be about 14 metres, 3 times higher than the maximum recorded there. However, if it's a tsunami wave, it may only has to be just over 3.5 metres high. If we look at the other relationships here, you can see I've drawn a line on this graph showing a relationship. That in the outer Bristol Channel, the boulders indicate smaller waves, and in the inner Bristol Channel, they're getting larger, and by the time we get to the Severn Estuary, they're the largest. That relationship runs counter to the storm wave patterns that we see. For storm waves, the biggest waves are in the outer Bristol Channel, the smallest are in the Severn. For tsunami waves, though, the biggest waves will be in the Severn estuary, and the smaller waves will be in the outer Bristol Channel. It shows us that the geological evidence indicates that this is far more likely to be a tsunami than it is to be a storm surge. Because a storm surge would have a different pattern. So there is a very strong chance that the event in 1607 was a tsunami from the Atlantic Ocean coming up the Bristol Channel. Now, on its own, that's some interesting geology. Perhaps we have some type of mass movement, a submarine mass movement, possibly off the coast of Ireland, that's generated a tsunami back in 1607. Question is, though, why is this important? Is this just a topic of some historical interest? Well, if you think about a map of the Bristol Channel area, we can see, first of all, that we actually have a lot of settlements. A lot of people live in this area, particularly along the South Wales coast. And these areas are all very low lying. Cities of Cardiff and Newport, Swansea, Port Talbot are all really only within a few metres of sea level. But it's not just the population living in these low-lying coastal levels. Let me show you something that might be a little bit scary. The Bristol Channel is also home to several nuclear power stations, some of which are being decommissioned. Others, though, particularly at Hinkley Point, are still operating, and there's even a new one being built at Hinkley Point as this is filmed. Now, nuclear power stations are built in coastal areas to provide limitless quantities of cooling water. But we've seen from fairly recent history what can go wrong. The Sendai tsunami resulted in an explosion at the Fukushima nuclear plant that continues to contaminate the surrounding environment, has caused an environmental catastrophe because of its inability to cope with the effects of a tsunami. Would the Bristol Channel suffer the same fate if there was to be another tsunami? It really does beg the question, what should we do about this? What's the level of potential risk here? Could this happen again? When would it be likely to happen again? What then? How could we prepare for this? Do we need to prepare for this? It's certainly something we need to think about. The evidence from history, even if they didn't quite get the years right, is clear. This event happened. The geology suggests very strongly that it was a tsunami event rather than a storm surge. Storm surges we're now in a far better position to predict. Can the same be said for a tsunami, particularly one caused by mass movement? And if this is going to happen again, what can we do about it? How can we prepare? How much would it cost us to prepare? Now, there is another documentary that goes with this that, um, if you want to find out more about it, is well worth watching. But as we see the sunset over the Severn Bridge, this event happened because of the geology. We see the evidence for it within the geology along the coast. We need to think about what that evidence actually tells us. And as a geohazard, what does it perhaps predict about the future? Now, as tsunamis go, it's not a big one, nor is it a very frequent one compared to perhaps the tsunamis that are experienced around the Pacific Ocean, for example. But clearly, there is some level of risk. It's up to us as geologists to determine the level of that risk. Now, what we need to do perhaps then is contrast this with a much bigger event. But that's for another lesson. I'll see you then.